Welcome everybody to the 13th monthly colloquium of the Hellenic Astronomical Society. And it is a great pleasure to have with us one of the senior members, founding member of the Hellenic Astronomical Society, Dimos Kazanas from the East Coast, from NASA Goddard Space Flight Center, who will be talking to us about warm X-ray absorbers, the Rosetta Stone of AGN phenomenology, with a question mark. So what I'll do before giving the podium, the virtual podium to Dimos, I would like to say a few words about him for those who do not know him. Dimos grew up, or he was born actually in northern Greece, in the beautiful city of Kavala. And then he moved to do his undergraduate studies to the University of Thessaloniki, because at the time the University of Crete was not founded. So that's why he chose that, because it was the best place.
For sure.
It was the best place in Greece to study physics at the time, as many of the senior people of the Hellenic Astronomical Society used to claim anyway. And then he graduated and he moved to the University of Chicago, where he did his PhD. And I actually checked to see what his PhD thesis was on. And it was on, I was surprised actually, and I closed the window. I think it was on neutrinos.
Yes. Neutrino-mediated shocks in supernova.
Yeah, exactly. I didn't know about that actually, because I had heard of Dimos originally from the work that he was doing in high energy astrophysics at the time that I was a graduate student, but also for the fundamental work that he had done on cosmology and inflation right after his PhD, which following his PhD, he actually did the military service and then went back to the land of the free and the home of the brave, but he was wiser and he didn't move to the Great Plains of the Midwest, and he stopped very close to the Atlantic Ocean, where the winters are milder, even though, and the summer is more humid. And he has been there ever since, reaching the goal of the average Greek in the US, which is the most difficult place to do it, to become a civil servant, actually, Goddard. This is practically impossible to achieve in the US, but Dimos did it, and he had a spectacular career with many fundamental contributions, and this was recognized by a number of awards and visits, and the most well-known on this is the fact that he's a corresponding member of the National Academy of the Academy of Athens for the past 20 years now, actually. So it is a great pleasure to have him with us as a speaker this time, because he attends the colloquia regularly, and we're looking forward to your talk. Thank you.
Thank you, Vasily, very much. Well, I mean, some of these things were not by choice, but by circumstance, but nonetheless, thank you very much for the kind introduction. I hope that I will give you something of interest to listen this afternoon. So before I do that, let me kind of give the names of my collaborations. Keigo Fukumura was at Goddard, now he's at James Madison University. Chris Rader is still at NASA. Keigo has done most of the photoionization calculations that I will show. It happened to be, Hudbihar is at Technion, but he is expert in X-ray spectroscopy, and happened to be at Goddard at the time that Keigo was trying to basically use photoionization calculations of the MHD winds that Ioannis got in his thesis. So we found out that his results they basically fit very nicely with what we were planning to do with, so he's a co-author in a number of papers, although we haven't co-authored anything for a while right now. Now the same stuff, I don't know if I'll have time to really go about that. The same structures, I have application in blazars. The blazars basically are something like all the other AGNEs, except that they have a jet along their axis of symmetry. And also I've done some work on the same structures, namely the winds I'm going to talk about, with Arka Sarangi, who was a postdoc with Eli Dweck, and we calculated basically dust production in in AGN tori. And I'll just say right up front that the AGN tori are simply the outer parts of the same MHD winds that basically emanate from the entire accretion disk of AGN, not only AGN, galactic sources too. Here is the conclusion I'll give you up front. AGN and galactic sources, well, any accretion problem that involves mainly scattering and free fall depends on only one parameter, the dimensionless m dot of the flow, as such as it is. What makes a difference is the thermal properties, which depend on the absolute scale. So in the AGN, they put lots of luminosity in the optical UV, while in the X-rays in the 1 keV region. On the other hand, the hard X-ray part, which depends only on scattering, they're identical in both galactic and extragalactic sources. So I already told you the conclusions of this talk, but let's continue. So here is the typical picture of an AGN. It's compiled backwards. We know they have, there's a black hole, here's a black hole at the center. There is line emission, so we put some line emitting clouds, and there is a accretion disk somewhere there. And of course, now we know there are tori, and therefore we put a molecular torus there. And that's the picture that Yuri and Padovani put forward about 25 years ago, and everybody still uses. And this is simply a cartoon in the same way that a Donald Duck is a depiction of a duck. That's basically it. So, of course, all that we try to understand from the spectral aspects of them, because we cannot resolve them, although recently we're able to resolve in radio with interferometry the accretion disk in the black hole, and I don't know if we understand anything about that, but that's a subject of a different talk. So here's a typical spectrum of these accretion disks, of these objects. They have optical UV, presumably comes, well, we'll discuss that a little bit further down. And of course, we also have the galactic sources, which have similar disks. Now, I'm sure they have tori, but they're highly ionized. That's why we don't see them. And hopefully I'll have time to discuss why we don't get dust emission in galactic sources. So here's the spectra again. Let me just zoom a little bit in this picture. There's X-rays. They all have X-rays. So there's something unique about the X-rays. Although we think that there's accretion disk, which meets, of course, in what we call now the UV bump. They're always X-rays. And, well, the idea is that we have a corona. Like the solar corona, we have a corona there that produces X-rays. My feeling is that this is not the correct picture. And hopefully I'll try to give you reasons for that. And there's, of course, the infrared from the torus, which, as I said, is a disk wind. This simply reprocesses the amount of X-ray UV that's produced near the black hole. Now, what this picture doesn't show is that, all right. Oh, I'm sorry, here is what, in order to characterize the spectra, we have to really give, they're more or less flat in UF-nu, as you can see, between 10 to the 12 and 10 to the 18 hertz. The range is, so we have now here 6 decades, and here we have basically 1 or 1.5 decade in the vertical range. So the spectra are more or less flat in UF-nu. However, there are particular features, and since both UV and X-ray come from the innermost part, we need to separate the relative importance of those, and we call that alpha OX, which is the ratio of fluxes, the logarithmic slope of the ratio of fluxes. High alpha OX in absolute value means a lot of UV versus X-rays. That's the nomenclature, but they use the way they use that, it's as a negative, so that when people say high alpha OX, they mean small absolute value. I'll qualify it. high alpha X, high absolute value of alpha X means lots of UV for X-rays. So here again, the spectra, that's the average spectrum to the left, but there are differences. If you look at this particular one, it's a local Seyfert 5548. The luminosity is dominated by the X-rays, contrary to what we have here. On the other hand, we have this rather famous quasar studied by George Chartas, for which you can see that the optical UV is a factor of 30 times larger than the X-ray. So the question is, what makes this difference? And so this is the essence of this talk. The claim is that there's one parameter that really makes this difference in luminosities. The particular details, of course, one have to solve for. What this spectra don't show is something which is a very rather universal aspect of these sources, which are winds. About 50% of AGN are observed to have UV absorbers, which are blue shifted, which means basically we have winds. And also another 50%, they have X-ray absorbers. So winds are basically something that a universal, just a second. A universal feature of these sources. Here is the 4151. It's a well-known local Seyfert in the UV, has an absorption. And here's the famous object by that I just talked about, and has absorption in the X-rays. These absorbers now, if they interpret as iron, have velocities which are of the order of good fraction of the speed of light. And what George showed, that as the slope of the X-ray increases, the velocity increases, the apparent velocity. These features here shift to higher velocities. Now, with the launch of Chandra and XMM, we found there are lots and lots of lines. So here is a particular spectrum for, I think it's 3783. I'm not so sure which one it is, but you can see the entire series of silicon, the entire series of magnesium, and so on and so forth. So now let's put next to each other two spectra, one an AGN and one a galactic black hole. Galactic black holes, they do have absorption features, but not as frequently as AGN. My feeling is because they're more ionized. But this particular one, GRO 1655-40, it's a famous black hole source, at some point showed this whole series of lines. And the difference with the black hole candidates is that the signal to noise is much higher than it is for AGN. So if you want to fit something, you want to test your models, you better look at the galactic sources, but they don't show absorbers as frequently as the AGN do. So here's something that Bihar taught me. Why is X-ray spectroscopy so important? Well, the point is that the presence of or not of a given ion for any object depends on one parameter. That's called the ionization parameter. That's the number of photons, which is L over R squared, over the number of electrons. Or you can write it as the column density of the particular ion. So a particular ion lives in a given space of Xi. So iron 25, 26, the highly ionized iron with one electron or with two electrons, they live in regions that have very, very high X-ray flux relative to their density. As you move farther out, and presumably the density drops less fast than the density of photons, then you find other ions and so on and so forth. So the advantage of X-ray spectroscopy is that it can access all states of ionization, from neutral iron to highly ionized iron. And of course, similar for all other elements in the space of factor of 20 in X-ray energy. So the highest iron 26 is 6.9 keV. And by the time you go to 0.3 keV, you essentially have all the elements in there. There are other elements in the far UV, but we don't have access to that part of the spectrum. So by measuring now the column density of widely separated in Xi ionic species, iron 25, neon 10, which live in very different parts of Xi space, we can calculate more or less the density of the material that absorbs these ions along our line of sight. That I'll show you in the next transparency, this particular calculation done by Bihar. And at the same time, we can calculate the mass flux, because the mass flux is n square r times the velocity, and n square is L over Xi. So if we measure L, we know Xi from the presence of a given iron, and if we can resolve the particular feature, we measure V, and we can calculate the mass flux. And people who did do X-ray spectroscopy, in particular for this very well-known galactic source, GRS, which one is that? 1915 plus 104. They found to be surprised that the M dot of associated with neon 510, I think it was, it's much higher than what you need to power the black hole. So we'll talk more about that. This is a crucial aspect of my talk. So I show you all the mess that all the lines. So what would be hard did is say, well, instead of trying to basically try to fit every line, there are low ionization lines, intermediate ionization, high ionization. Let's assume that the column density is a power law of the ionization parameter. And now we can try to do a global fit just for this parameter P. So therefore, you take all this mess and you condense it down into a single parameter. And he did that. And so here, then you divide by the abundance of every ion to find the equivalent hydrogen density of the particular plasma that absorbs, that provides a given absorber at a given Xi. So here is the column density as a function of Xi for this particular AGN that he did for different elements. That's for iron. Then the yellow is for silicon. The green is for oxygen, and so on and so forth. And you can see there's some consistency that even though Xi varies over 5 decades, the column density is around 10 to 21.5. And he did that for this set of AGN, and you found that the Xi now varies between 0.2 for this particular one to 0.29 for AGC 3783. So you can see again that the ratio here is about 5 decades, and here's about 1.5 or 2 maybe. So there is something fundamental about the density distribution that produces this kind of regularities. So let's do some simple estimates. So Xi is n over r squared. We can write it as a column. We solve for the column, which is L over r Xi. And as we saw, at least in one of them, this is constant. If L over r Xi is constant, it means that the luminosity is given. R times Xi is constant, which means Xi goes like 1 over r, which means that the density, not exactly 1 over r, but close to 1 over r. And yet all these are winds. And yet the density profile is not 1 over r squared as you expect for the wind. Of course, the wind, if it's 1 over r squared, the Xi, both the density of the photons and the density of particles fall the same way, and therefore the ionization is constant. And you don't have variation in the ionization of the gas as both distance. And the column is very, very small if the density drops like 1 over r squared. We can calculate now where density of the wind drops like 1 over r, we can calculate the mass flux. And the mass flux is again n times r squared times the velocity. N times r squared goes like r to the minus 1, and multiplied by r squared and by the velocity, and we find out the m dot is increases with r. So the m dot in the wind now, in the wind is not constant, but it's increasing with radius. Well, that is true in Ionis's thesis work, and it was noted by Blanford and Bigelman, which you can say, how can that happen? Well, basically, most of the mass ejected before hitting the black hole. That's how it can happen. And of course, the flow must be two-dimensional. It's not a one-dimensional flow. Radiatively driven winds, of course, are essentially one-dimensional because all the lines of force emanate from a single point. Accretion MHD winds, like the Ionis and Blanford's, they come from the entire wind. There's a two-dimensional winds. That's why it's possible to have the m dot not dropping like 1/r squared. The same winds actually was claimed back. I'm not claiming that. It was Koenig and Cartier, and I fully prescribe to this proposal that if you go sufficiently far away, these winds, they'll be very cold and they'll be dusty, and they are actually the tori that we call an AGM. Oops, I'm sorry. If m dot goes like r to the 1/2, the kinetic luminosity of the wind still comes from the smaller radii because it's m dot times v squared, and v squared goes like 1/r. And they have roughly equal momentum per decade. Now, it is not exactly 1/2 as you will see, but it's close to 1/2. Maybe it's 1/3 and so on and so forth. The density is not exactly 1/r. It's at least the ones we can fit, 1.15. So here, if the wind covers 6 decades in radius, you better do self-similar solutions, which means that have some kind of density dependence, which is a power law, same for the magnetic field, same for the pressure. And of course, the velocity goes like r to the -1/2. And then you have the remainder theta degrees of freedom that basically you have to solve for. And that Ionis taught me that this is called the Grad-Safranov equation. Has a wind type solution. And once he solved that, that's from Ionis' solution, you find out basically the density as a function of theta. You can see it's an exponential dependence with a ratio of axial to equatorial about 10⁴. So from far away, these things look like tori. There's very little in the theta direction, in the near theta equals 0, and huge column around theta equals 90. And here's the velocities. The velocities the wind starts basically as it lifts out of the accretion disk. It rotates pretty much like an accretion disk, but then only when it goes past the Alfvén point, it becomes almost radial or parabolic, actually, in this case. So those are there's a structure of the winds. And here's a schematic that I'll show you. The density of the graph here is the equivalent proportional local column, not like density, because the density drops with r. What I show here is the column, very little column in the theta equals 0, a large column in the theta equals 90. These lines are the poloidal field lines. They're also toroidal field lines because as the disk rotates, twists those lines, and those are the toroidal field lines that we not show here. This is high ionization component, low ionization component. And out here, the density, you can calculate the temperature, and it's small enough so that you can call it, that would be the torus. That's a schematic. And this is the true solution of the same equations. Of course, this is in log space, this is in linear space. And here we show how we do the ionization calculations. We put all the X-ray spectrum at the center. We split the line of sight logarithmically into equal boxes, if you like. We calculate the ionization structure of each box, and then all the opacities, and they pass the radiation through those opacities. So what comes in the next box is something less than what came in, depending on the opacity. We use that output as input. Go ahead, Nico. Yes. We use that output as input, and we continue until we find basically the ionization along a given line of sight. As a technical detail, maybe I shouldn't really worry about the technical detail. Okay, I'll say that. The opacities near the center of the lines are very, very high, and you won't see anything. However, the shear in the wind provides a velocity gradient. So we, for those who are familiar with that, we use the Sobolev approximation to calculate the opacity as a function of wavelength. And if we don't do that, we have to use some turbulent velocity to broaden up the lines. Otherwise, you won't see anything due to the high opacity. So that's a technical aspect of the problem for people who work on these issues. So here is a fit now for this particular AGN 3783. Those are different lines that we try to fit with a try to do a global fit. I only showed 9 lines. We have another 9, which is another transparency. And with a global fit, we try to do, we assume that the density now is r to the minus beta, power law in density. And that is 1.1, we find beta to be 1.15. And there's a relation between the density beta and the value p that Bihar used in his parameterization. So beta is 2p plus 1 divided by p plus 1. So if beta is 0, if p is 0, like we was in one of the AGN, beta is exactly 1. For the highest value of 0.29, beta is 1.22. So the density for this particular AGN, which is this one, is we find it's 1.15. So for 1.2, so the bottom line is that the density along the line of sight drops slower than the photon density, which means that if you start with high ionization lines near the black hole, as you progress farther away, you get lower and lower absorption features, lower Xi, lower absorption features of lower ionization parameter. So as you go away from the black hole, the ionization parameter drops. So you get, instead of having high ionization ions like 25, iron 25, 26, you get the neon 10 and oxygen 7, oxygen 8. So there is a gradient, natural gradient in the ionization structure of this wind, simply because the density of the wind drops like slower than r to the minus 2. And you don't want to make it too steep. If you go like r to the minus 1.5, then this is a blunt for pain winds. They're not consistent with the observations we get, at least in some objects. Maybe in some objects, we start really collecting data along these lines. So with CRISM, probably we get more. And maybe in some cases, we do get r to the minus 1.5. We don't know. But the ones we've fitted so far, they are less than 1.5. So here is the ionization structure of, let's say, of such a wind for this particular object, the 3783. So what I plot here is the ionization parameter, in particular the distance, if you like. And out here is there's the column density, the hydrogen equivalent column density. And here's the velocity. The velocity, it's in log space. The velocity is a slope 1/2 curve. And you go very close, you still have some iron 26 and some iron 25, if you like, but not much. So as you move farther out and the ionization parameter drops, you get more and more and more iron. Then you reach a peak, and then you go too far out, then it's too little ionized and no more iron. So it drops very sharply. And if you convolve this curve with the velocity, then you get the absorption line profile. So that's what we got here for this galactic source. And all these absorption lines you have, they're computed exactly this way. We have to fix the normalization of the wind. And in this particular case, we also know the inclination angle until we get the right depth of the absorber. But each absorber here is fit with a one parameter beta and one parameter N0. We don't fit individual lines separately. And you can see the fit is reasonably good. And the width of the line has to do with the shear in the velocity, in the wind velocity. And this is the highest signal to noise spectrum we have for any absorber source, simply because the source is bright. So here, let me show you how we calculate the particular line, the iron 26 Lyman alpha line. So here we have it in wavelength, not in energy, because HETG in Chandra works in wavelength. So as you're very close to the black hole, high ionization, then you have absorption high velocities because the velocity is high near the black hole. But the column is small because you're highly ionized. As you move farther and farther out, yes, you get more iron 26. You produce a deeper absorption here, but it's not as blue shifted. And as the more you go farther, the farther you go out, then you basically slowly form the entire line. And that's what you see. The red line is what you see when you go to infinity. And the same is true for the neon 10, but it's not so easy to see this particular shape of the line. It's seen clearly here. And now if we fly CRISM, then this is the iron 26 line. All this feature will appear a lot better. So let me show you a zoom in here. And you can see now, this is in energy, shorter wavelength. There's a curved wing towards the higher energies and sharper and towards the lower energies. That's what the iron line is in Chandra, as I show you, but that's how it would appear in the, this is simulated 45 kilosecond CRISM resolve observation of the particular source with the flux that we got for the Chandra observations. And that's what you're going to get for a 10 kilosecond Athena observations with the X-ray calorimeter. So you can see the shape of these lines. If they resolve, they will tell us something about the structure of the winds that we have, maybe more accurately than what the models predict. So let me go quickly here through the accretion disk theory. I'm sure that most of you know, and if you don't know, it's all that is taken from Novikor and Thorne. We have now accretion disk requires a transfer angular momentum. So here is the angular momentum transfer, and has to be basically it's affected by the stress energy momentum tensor, which is of course proportional to the pressure with parameter alpha. And we have also hydrostatic equilibrium in the z direction. That's all well understood. Now we can calculate, once we have TR phi, the stress energy momentum tensor, we multiply by the shear in the disk, and we calculate the energy produced in the disk. And that has this particular expression. There's a 3 that comes from that 3. And you can integrate this from the ISCO to infinity, and you get how much energy you get produced in the disk. And this is factor of 3, and it's in all books. It's 3/2 times m dot gm over r1. R1 is the inner disk radius. On the other hand, you can calculate easily how much potential energy you leave if you start from infinity all the way to r1 is gm m dot over r1. And of that, only half, because of Virial theorem, is allowed to be converted to heat. So if we only consider material energy that comes from infinity to this particular radius, we only have 1/2 gm m dot over r1. But from the accretion disk equations, we find 3/2. So where is the other factor of gm, 1 gm dot over r1? Well, that extra comes from the energy transferred by the viscous torques. It's important to bear in mind that besides angular momentum, viscous torques transfer also energy, mechanical energy from the inner part of the disk to the outer part, because that's the way angular momentum is transferred. And if you followed Blanford's talks anytime recently, he tries to make that point very vociferously for blazars mainly. But the energy transfer is the omega times the torque. And that is actually GMM dot over R1. As I said, I'm not saying anything new. All that is in standard books. Maybe in particular, this particular formalism I got from Novikov and Thorne. So we can always find that. The important thing is that it is assumed that the entire amount of this energy is converted into heat. And I think that assumption is not correct. Now, once you do that, then you can calculate the temperature as a function of distance and becomes out of the -3/4. But you realize that this you will get irrespective of the value of this factor in the front. And of course, now you know that for a galactic source, this temperature is approximately 3 million degrees. But for quasars, with and it depends on the mass of the black hole to the 1/4 power, goes down to 30,000 degrees. And this essentially indicates what I said at the very beginning of my talk, that all these structures are essentially scale invariant except for thermal effects. Thermal effects depend on the absolute scale. If you have absorption that thermalizes energy, then the result depends on the absolute scale. But otherwise, the dynamical structures are presumably scale invariant. So here I repeat the point that not all the energy transferred by the viscous stresses can be dissipated in heat. And in the presence of a colloidal magnetic field, there's a possibility that both the angular momentum and the non-thermalized energy are ejected in the z direction along by the magnetic field. And those are the winds. So despite much numerical simulation, the details of such proposal remain rather obscure, simply because there's not enough dynamic range. I mean, people use the MRI, but they have a big torus at some radius, and then what you call the accretion disk spans only a factor of 10 in radius inside the torus. You cannot, I don't know, my feeling is we cannot really see very clearly what's going on there. And if we wanted to understand all this in detail, then we have to have a combined disk, magnetic field, MHD, wind, dissipation, and dynamics, all this mixed together. And I don't know if that the current simulations can take all that in. I'm not terribly familiar with those. However, the only manifestation of all this detail comes out in the wind, comes in the wind processes, in the wind properties. So we have something going on, but eventually we see that we have winds. And winds we can measure. We cannot measure the processes inside the disk, but can measure the process of the wind. And presumably the two are related in a way that is kind of opaque right now and maybe difficult to calculate. So now we see the winds have mass flux that's higher farther in, that farther out or farther in. And therefore, that means that you have a certain amount of material that be accreted, and you lose most of the material on the way. It's not difficult to understand why this is the case, because if you want to transfer angular momentum from a given gas, then you have to take angular momentum from some part of that gas and give it to the other part of the gas. Well, that means that because all the radii are all the velocities of the same order, then this part that will get the mass, you have to lose that part. You cannot accrete that part. And I had this argument with Canizzo, the late John Canizzo. He didn't believe me, and he did his calculation, and he came back the next day. He said, yes, that's true, because he never worried about what happens to the material that flows out. He only worried about what goes inward. But anyway, So the accretion rate must decrease with R. And therefore, for a given steady state situation, there will be a particular radius in which the local m dot now, so the m dot in the disk now is not constant, decreases inward. They'll become smaller than alpha square. Alpha square is the viscosity parameter. Well, that is, when m dot is smaller than alpha square, then that's a condition to have an ADAF. ADAF is basically disks that have cooling time scales which are longer than the inflow time scales. And therefore they cannot cool, and the protons become virial and the electrons become, well, virial. They try to get energy from the protons so you can get a hot inner part of the disk. So therefore, as the overall, so now all of a sudden now, instead of saying that the X-rays come from some corona, which I have no access onto it, now the X-rays become part of the entire dynamical accretion process, and therefore tells you something about the inner part of the disk, not something about a magnetic field structure which you have no access to, which produces the X-rays, like say the sun. So now the X-rays and the big blue bump, they must be related. And as if we insist that they increase the entire m dot of the entire flow, then we see that this transition radius should probably move inward. So, and we can do some calculation from that. Let's assume that the m dot goes like r to the 1/2, as I said. Probably goes a little, it falls a little, it doesn't increase as fast, 1/3, but I've used this expression for 1/2. Then the transition radius is such that m dot times the x transition to the 1/2 is equal to alpha square. So we can basically calculate the viscous disk luminosity, which is m dot over x, as you expect, integrate over the disk, and it gives you this expression, and you can calculate what happens interior to that transition radius, which of course is m dot over x, but now because the efficiency of ADAF is proportional to m dot, it's m dot square over x. And so this is the X-ray bolometric here, and this is the black body bolometric. And we can basically take the ratio, which is the ratio of these two square parentheses, and you can see what it looks like. It looks like this. At a large radii, if the transition radius is a large radii, then you can have the X-rays dominate the blue bump. And from this case, by approximately equal, I would say that the transition from the blue bump to the ADAF is at around 70 to 100 Schwarzschild radii. On the other hand, you go to the southern AGN, which of course we don't have measurements here, but we can see that this is part of the disk. And this ratio now, the blue bump, if you like, to X-rays, about 30. This must be way out here. It means it has squeezed the X-rays very, very close to the horizon. And that's because of one parameter, the global m dot. Either m dot, assuming that m dot goes like x to the some power 1/3 or 1/2, either you change the m dot at the inner edge or you change the m dot at the outer edge. Assume, of course, that you have this power law dependence on m dot. And this was all known way back in 1997 by a paper by Essin, McClintock, and Narayan, and they tried to explain the phenomenology of galactic black holes. The interesting thing about galactic black holes is we have the same black hole for different luminosity stages, and therefore we don't have to do statistical analysis of, oh, this AGN is low luminosity and this is lower Eddington, this higher Eddington. We have one black hole, and we can basically follow the spectrum. And this is the what's called the low Hart spectrum, is dominated by the high energy X-rays at 100 keV. This quasi-thermal component is what you call the equivalent of the blue bump, but now it's in the X-rays. As you increase the luminosity, you have the hard state, which means that this piece dominates over the X-rays, and all the I don't know what to make with the ultra soft state. Nikos maybe can tell us. And then eventually you have some cases where you have a very high state, which is close to Eddington. And of course, then you expect the disk to be thick. So the hard state, you have this particular structure we discussed, the transition radius at, I don't know, 100 Schwarzschild radii or 50 Schwarzschild radii. You go to the hard state. Now, this piece, the X-ray piece, the hard component is squeezed very close to the black hole, less emission. Most of the emission is by the quasi-thermal component, and this is the state close to the Eddington. The whole disk is puffed up. Of course, all that has manifests on the timing properties of the black hole. In this particular case, you have the material try to squeeze in. Yes, you sent in some flux, which becomes X-rays. And so you have basically random shots that come in there. And the spectrum of the random shot is a white noise with a quadratic cutoff. And here we plot the power spectrum times the frequency. So the white noise is rising here. And because the disk oscillates at that point, not surprisingly, we also have a QPO, which as we increase the luminosity, this inner edge moves closer and the QPO moves to higher frequencies. And I'm sure that Nikos is totally familiar with that. And it has an this whole thing has an explanation into this two-component model. The reason that you cannot work that with ADAF is because, as I said, ADAF is a global condition. Either you have m dot smaller than alpha square, or you don't. In this particular case, what the winds do allow the m dot to vary in radius, and therefore there is always some inner radius which fulfills this condition. And of course, the accretion disk has a current sheet at the an equator, and therefore that can heat up the material, and you can get this particular structure that theorized by Essin et al. So what's the difference between AGN and galactic black holes? Well, so here, as I said, the disks are identical. Here are the two identical disks. The only difference between the two is how much ionizing luminosity we have. In AGN, we have this so-called blue bump, which is the equivalent of, we are in the, if you like, in the soft state of galactic black holes. And the X-rays are not really, and that determines more or less the normalization of the matter density. And the X-rays give you the normalization of the ionizing photons. In AGN, the ones that we discussed earlier on, the Seyferts, the X-rays dominate the ionization, and there's an ionization front. The density drops, but the photon density drops faster. So there is an ionization. Everything is highly ionized here. The ionization front, which tells you the velocity of the innermost ion 25 or 26, and ranges between 30 and 100,000, between C/30 and 10,000 kilometers per second. Tom Basic calls them UFOs. Now, if you go to galactic black holes, the entire SED, including what we call the UV bump, is now in the X-rays. It's all in the ionizing part of the spectrum, and therefore ionizes everything out to very, very large distances. And therefore, the corresponding velocities are small, 300 to 1,000 kilometers a second. And that's what we saw in the GRO 1655 - 40. So this is the big difference now between AGN and galactic black holes as far as the absorption features are concerned. We don't see high velocities in galactic sources in general. Now, who knows, maybe in the future, somebody will find some high velocities. I cannot explain that. The model I have is propose here has two parameters, N0 and beta. And if something happens to some particular AGN galactic source and shows 10,000 kilometers per second velocity, I don't know what to do about it. It will not be along this. We have to use another model for that. So we can see the same thing now for galactic, for extragalactic black holes. We can play the same game. Velocity here, ionization parameter there. I want to show you the what happens if we put, besides iron, carbon-4. Carbon-4 is important because we see it in BAL quasars. BAL quasars have carbon-4 velocities, which are 10,000, 30,000 kilometers a second. So here the velocity is in linear space. And I have, again, the ionization structure, iron 26, then 25, 24, and so on and so forth. But the carbon now comes at much smaller velocities. Here's the velocity of the carbon because it's at the lower Xi. The lower Xi means here's the velocity. The velocity of iron is this, very high. The velocity of carbon is around 0.1 C in this case. And now don't be scared with this. It looks complicated, but it's not. This diagram is not very as complicated as it looks. Just focus on the dashed lines. The dashed lines tells you how the velocity changes as you change alpha x, as you increase the X-ray luminosity versus over the UV. When the X-ray luminosity is small and the UV luminosity is high, then we have the high alpha x in absolute value. The velocities are very, very high because the ionization front is very, very close to the black hole. As you keep increasing the X-ray luminosity and decrease the UV luminosity, then this brings this line over along here. And this object we call BAL QSOs. The same, this is for iron, and this is for carbon-4. For iron, the velocity is 0.8 C. For carbon-4 is 0.15 C. But then as we make the UV less important, we go from BAL QSOs to Seyfarths. And those are typical velocities of Seyfarths for both for the iron and for the carbon-4. So this, as I said, this may look complicated. It's not as complicated as it looks. The bottom line is that the lower the UX-UV flux ratio, the higher the velocity. So the less X-rays you have, the ionization front is closer to the black hole, and therefore you have higher velocities. This seems to be borne by observations. And of course, you can change the X-ray flux by making the X-ray spectrum steeper. And those are the data that George Chartas did. As gamma increase, that's this line. This line has a fixed alpha x, but increases the gamma. As gamma increases, the spectrum becomes steeper, the velocity becomes higher. So we have now, let's see how much time we have. I'm not going to go through all that. We talk about absorption lines, but there's also emission lines. And emission lines are, well, they're more complicated, but it's easy to calculate luminosities because all you need is the n square v, that's called the emission measure, multiplied by the recombination parameter that gives you some scale, that's 1 over time in some sense, and the energy of the H alpha line. And now you can calculate how much n square v is in this model. The model has assumed here r to the minus 1, and you can find out that basically n square v goes like m dot square, dimensionless flux in Eddington units times the mass. You can see therefore the ratio of L to M is constant in that sense. And here's data from Osterbrock's book, Astrophysics of Gaseous Nebulae and AGN. And you can see that the line luminosity is proportional to the continuum luminosity. And when we go to galactic sources, then this proportionality changes by maybe a factor of 10, okay? And I'm asking the observers to always, observers usually when they give you H alpha for the galactic sources, they give you the line of the continuum at 1, and they show you how much above the continuum is without giving you the absolute values. And therefore, it's very hard, unless you do the observations yourself, to calculate, to put galactic sources on this diagram, but nonetheless, this whole scheme works for the emission line luminosities, if you like, roughly. They cannot be very tight in this case, but this linearity is kind of remarkable, I would say. I have now a few things left. I don't have enough time, but I will just touch upon them. The AGN tori and the dusty winds. I already told you that the tori, they have to be winds because the temperatures are only 100 K. The thermal velocity is about 1 kilometer per second. However, at the distances of 1 parsec, the virial velocities are about 300 to 500 kilometers a second. And therefore, if they were to provide so much covering, then the random velocities, there were clouds, they would collide within one time scale, one dynamical time scale, and it will not be that cold. So these must be flows which are directed flows and don't collide with each other, whose elements don't collide with each other. And we use that model basically with Sarangi and Elie Dweck, to calculate how much dust we can produce. And the dust is proportional, the amount of dust you can produce is proportional to the mass of the black hole. The larger the black hole, the more mass, and also depends strongly on the mass flux in Eddington units in the wind. And you can, of course, in order to produce the dust, first of all, you must be beyond the lines, sublimation, dust sublimation radius, and the flow velocity must be longer than the chemical equilibrium time scales. And this produces in R m dot some kind of restrictions. And you can see that you can do that for 10 to the 7, 10 to the 8 solar mass black holes. But if you want to go to 10 solar mass black holes, then this is possible only for distances larger than 10 to the 7 Schwarzschild radii out here. Of course, 10 to the 7 Schwarzschild radii in a galactic source, you hit the binary companion. So we don't expect dust formation in galactic sources, even though the structure of the winds is not very different. It's just the radiative properties are very different. Well, all right, I have a few minutes. I will not go details of the blazars, but I will really have to mention that. The difference that, as I mentioned earlier, that what really makes a blazar is, besides the same wind, which we assume is there is also some non-thermal component along the axis or close to the axis. Maybe a current sheet very close to the black hole. That's my personal preference right now. But what really happens here is the torus, the torus and the entire wind has a scattering depth, which is not 1, it's smaller than 1, but it's considerable. And therefore, lots of the flux out here you produce near the black hole, instead of chase the outflowing, relativistically outflowing material, which it will be irrelevant, it finds the material by scattering into the disk at some large angle. Scattering a large angle means that all these photons that are scattered here, they appear in the front of this outflowing blob. And now the magnetic field and the scattering and all these things are related through the disk structures. So I don't want to go to the details here, but the magnetic field is in some kind of flux, equipartition fraction of the disk material. And the wind Thomson depth is also related to the m dot in the wind and m dot in the disk. And therefore, when you put them all together, then you find out that the number of parameters you need to fit the spectrum reduce substantially. And here we have now some runs that Stella run. And for low ionization, for low m dot means that the wind is essentially transparent. We only have the synchrotron self-Compton radiation. And the spectrum has a break which is at rather high gammas. in the electron distribution function. As you increase m dot and you divert some of the continuum luminosity into the blob by scattering on the sides, then this, I'm sorry, this particular break in the spectrum moves to lower energies. And the more you increase the, so this is for 10 to the minus 3 m dot in units of Eddington, and this is 10 to the minus 2 and 10 to the minus 1. We have to read the details here, I don't remember. But then you can see that this is the Fermi band. And as you increase the m dot, the Fermi band, the spectrum shifts through the Fermi band from being hard to being roughly flat to being soft. And at the same time, the peak emission of the synchrotron component shifts to lower energies. And that's what we have here, the peak emission of the synchrotron. When it is at high energies, that's called Markaria 421, it's the gamma ray spectrum is very hard. And as you increase the m dot, if you like, the dimensionless m dot, you go to FSRQs, then the break energy goes to lower energies, and therefore the synchrotron, corresponding synchrotron energy, which is plotted down here, goes to lower energies, and the gamma ray spectrum becomes rather hard. I understand that it's kind of hard to swallow, to digest all that in such a short time, but the point I want to make here is by having photons from the central source scattered on the wind and intercepted by the blob, we can reduce the number of parameters we need to explain this phenomenology of the blazar spectra. So I think I pretty much have covered everything. It's rather quick, and I understand there are too many notions in there, but the fundamental notion here is that there is a wind that has m dot, which is increasing outward, and it can do all sorts of things, including scattering photons into the outflowing relativistic blob and producing dust, and of course explaining all the absorber phenomenology. So here's my conclusions. There's mounting evidence of ubiquitous presence of outflows which associate with accreting black holes. Okay, that's fine, we accept all that. As promoted in this talk, the wind appearance implies dynamical properties in the wind that can affect the dynamics of accretion, I think through the radial m dot dependence, which in turn affect the SEDs, which in turn affect the wind's appearance and the phenomenology, and possibly its dynamics. If there is a lot of radiation pressure, that has to be included in these calculations, which of course is not here. So far, we only use the whatever Ioannis has produced in his thesis with different values of the density parameter. So all these issues essentially are related. So but the wind, therefore, the spectral properties of the wind is simply an epiphenomenon of the entire flow structure, which includes, of course, the accretion disk structure, because whatever comes of the wind has to be, after cooking everything up in the accretion disk, through the rotating poloidal magnetic field that spans 5 or 6 decades in radius and about 8 to 10 decades in frequency to complete what we picture, what we call AGN. So AGN is not just a black hole. It's the entire wind all the way from R equals 1, if you like, to R equals 10 to the 6. And that distance is determined by the black hole influence radius. When the velocity in the spheroid, because all these black holes live in spheroids, they don't live in thin accretion disks that extend 10 kiloparsecs, they live in spheroids. When the velocity in the Keplerian velocity wind becomes comparable to the velocity dispersion in the spheroid, that's when the accretion disk stops. That's where we'll collect all the gas to send it to the black hole. So maybe the M sigma relation that some of you may have heard, that the mass of the black hole knows about the mass of the spheroid, the velocity dispersion of the spheroid. But the dispersion velocity of the spheroid is also related to the mass of the spheroid through the Faber-Jackson relation. So all those things are not separate entities that they can be studied independent of each other. But eventually we have to have an entire picture that covers all of that. And what I presented here is some kind of view from afar of how all these things are related, and with the wind properties, which being the epiphenomenon that really tells us something about what's going on in the disk, what's going on with the energy transfer, angular momentum transfer and escape, and so on and so forth. As I said, crucial in all this picture is the presence of magnetic fields. Well, I mean, I'm preaching to the choir here. Yannis and I have worked on the cosmic batteries, so maybe all these magnetic fields are also generated. They're not independent, put by hand, but they've been generated through the action of accretion. That's the what can I say? That's our view at this point. Finally, well, the absorption lines are nice, but they tell us only a small fraction. They span only a small fraction of the entire phase space of these flows along that part, along a line of sight. To probe the entire phase space, we need to focus on the emission lines, and that's also another can of worms. You probably know that people talk about clouds here and clouds there. Well, I'm not convinced that, well, there may be some clouds, but if I can simply produce that relation that Osterbrook has in his book with some analytic formula, I start doubting about clouds, and we have to really also pay attention to the emission lines. And I think I'll stop here, and thank you very much.
Thank you very much, Dimo, for this exciting talk. Very dense information. If there are people who are interested to ask a question, please raise your hand, and or just yeah, Nick Lafis.
Thank you, Dimo. Very nice talk. A lot of material.
Yes, I'm afraid it's a lot of material.
As you said, even for experts, it was a lot of material.
Yes.
So,
more than one idea in there. It's unfortunate.
I know.
That,
okay. Let me. I think I've told you that in the past that I like very much the fact that the density goes as roughly 1/r, and this has, going back to the very first paper of yours, Kazanas, and Titarchuk.
Yes, that's right.
This has nice properties, which I used them later on in a parabolic outflow.
That's fine. Yes,
and I will not discuss that. I want to ask you the following question. I am not an expert in AGN at all. So I will stick to black hole X-ray binaries.
Yes, that's fine.
And since there is, you can scale by the mass, then just you come to my territory, then I to yours. Okay. These transient black hole X-ray binaries have luminosities close to Eddington.
Yes.
Let's say easily 1/10 of Eddington.
Right.
The luminosity, the X-rays come from close to the black hole.
Yes. Yes, of course.
Very. Yeah, that's right. Otherwise, you cannot. So we take the accretion rate as a proxy of the luminosity.
Yes.
But that is the local accretion rate. And if the accretion rate increases as r to the 1/2,
yes.
If I go 4 orders of radius out, which is not too far, I will have 2 orders of magnitude more accretion rate. But
right.
2 orders of magnitude more accretion rate is super Eddington. And then
No,
What do
but
you mean?
there's no luminosity there. It's a super Eddington if you convert the accretion rate into radiation. The radiation comes, as I told you, the E dot comes from the small radii. So the radiation comes from the smaller radii, and the X-ray, and the luminosity also comes from the small radii.
But
Because
but the disk is shining
Yes.
Optical radiation further out.
Yes.
So some radiation is released.
right, there is.
further
So
out.
do we have a lot of optical emission in this object? I mean, again, assuming that the M dot is steady state, you don't allow to vary in
Okay.
time and in space. Let's assume we achieve steady state. The local luminosity goes like M dot over R. If M dot goes like R to the 1/2, M dot over R goes like R to the -1/2. So the question now is, if we go to the optical emissions for galactic sources, can we and assume that we see this radiation in the optical, can we connect that to the X-rays? It should be smaller than the X-rays because the luminosity is still smaller as you go farther out. It just doesn't drop like 1 over R. It drops like it drops like R to the -1/2. But it's still smaller.
Okay. I was wondering if the assumption that you have a Shakura-Sunyaev disk at these high accretion rates is justified.
Well, we
Further
have to.
out- fur-
We
further
have.
out.
Yes. Now, I had this discussion with Ferreira about a month ago, maybe a little more. We see the winds. We don't quite understand how the angular momentum transfer from within the wind goes from the within the disk goes into the wind. This details. Ferreira has models and so on and so forth. We discussed his models a little bit. He cannot make that much of M dot. He said, I need some additional entropy dropped into the system. And of course, there is some entropy you can get. There's a current sheet in the equatorial plane. There are currents that want to basically confine material onto the disk, and the magnetic field annihilates. Who knows? I don't know. As I said in my concluding remarks, the winds are only an epiphenomenon, which somehow we can calculate M dot for the wind because all you need is the X-ray luminosity, Lx, and the Xi, and the velocity. And if you can resolve a particular line, you can resolve the velocity, you have the velocity, and you know that the given ion lives in this parameter in Xi, so you know Xi, you measure L, and now you have the M dot. And that's why, what's his name? Joy Nielsen, he was surprised that the neon 10 outflow mass flux is much higher than we need, the mass flux, not the luminosity, the mass flux higher than we need to power the black hole. Yes, that's what happens. I mean, the way to, it's unfortunate that only with spectroscopy you can calculate how much mass flux is in the wind. Now, most people still believe that the winds are radiation driven, and that will not give you that gives you the wrong AMD, absorption measure distribution. I mean, the column is a function of distance. It's totally different. It actually increases outward, but I forget it now. The ionization increases outward instead of decreasing outward. But anyway, that's another story. But yes, I understand all these misgivings that you have because it brings everything upside down.
Okay, thank you, Dimo.
Sure. At least I have one question. Nico, thank you. Usually nobody asks any question.
Can I ask you one question, Dimo?
Yeah, go ahead, Nico.
Yeah. So first of all, thanks for the talk.
You're welcome.
I'm not a specialist, even less than Nikos Kilafis in that topic. But I was wondering about the question mark in the end of your title.
Yes.
So finally, after listening to your talk, I'm not sure if you have given an answer or not. Are these X-ray absorbers a Rosetta Stone or not?
Well, as far as I'm concerned, yes. That's the epiphenomenon that relates to everything else in the disk, not only
Yeah,
near
but the
the black
Rosetta
hole, but
Stone means,
but
the Rosetta Stone means that they give us a clear information.
I'm
Is the
sorry.
situation so clear?
Well, if I confuse the audience, I'm sorry about that. Yes, I try to make it clear in the concluding remarks. The warm absorbers or the absorbers now, there's only, as I said, an epiphenomenon. They don't tell you, they don't probe themselves the physics of that produces these winds in detail. But the wind solutions are well described once you give a, now Yanis maybe can comment on that. Once you give the accretion disk and you put the colloidal fields there, then the Grad-Safranov equation and all the solutions that Yanis and Blatford and Payne found, they describe well very well the wind accurately, but they don't describe what happens in the disk. The only thing we can say, because we see the wind mass flux increases outward, it must decrease inward, and then the rest follows. I don't have all the details, but I can see now, if I have a mass decreasing inward, that the inner part will naturally convert into an ADAF, and therefore the X-rays. For the X-rays, I don't have to theorize about magnetic field lines that annihilated this patchy corona and non-patchy corona, and it covers the disk, or it does. It's the inner part of the accretion disk. And therefore, its dynamics is related to the dynamics of the entire flow. That's all I can say. And this is a corollary, if you like, if I stick to my view that the wind properties tell you something about the flow in the disk. It may not be true. I don't know. But if it appears reasonable at this point, if that is the case, then we tie now the tori, the absorbers, the blue bump, and the X-rays into a single flow with properties that depend on small number of parameters. If you don't have small number of parameters, you don't understand anything. If you need 3 parameters for the blue bump, and 3 parameters for the X-rays, and 3 parameters for the near IR, and 3 for the far IR, then you have 12 parameters. And with 12 parameters, you know nothing, really. So that's the what I find, and not to measure blazars, where its model needs 7 parameters. So in this particular case, we have now, we condense. I don't say I understand everything, no, but we have a framework in which all those things seem to fit reasonably well. I'm sure there are details that they don't. Astrophysics have their own variations from object to object, that's one thing. And then, of course, there's local variations in the local physics that also make some variability. But the very fact that we find a general spectrum which fits more or less okay, it means that something must be correct in there. We need to develop more observations, how all these things, both the timing and the spectra, change together. And the nice thing about the galactic black holes is that you don't have to do statistics. You have everything happen in a single black hole. So you find out that when there's a Q diagram that I'm sure Nikos can tell you lots about it. I didn't try to put it in this talk. So it shows there are systematics across the galactic sources, which follow more or less the same qualitative behavior. Not all of them exactly the same, but qualitative. They start with very hard, and then they become soft, and then they go back to hard again. Now, we had a paper with Nikos and Yanis and Dimitri Christodoulou, which explained all that, and the referee wanted us to provide numerical simulations. But you don't need to numerical simulations for all these things, but because it's very hard. You don't have dynamical. It would be nice if you can have the dynamical range, so you can basically give one parameter, and then the simulation provides all this information. We don't have that. Now, I don't know if Yanis is there. Maybe he can make a few comments on that, on these issues. if he wants to. If he's still there, or he had to go home.
No, you said it all, Dimos. I will not comment now.
You'll not comment.
No, I agree. I agree completely with your comment that we have so many, such a large dynamical scale in this range in distances that we cannot do that in a simulation.
Yeah, you cannot.
You have to use arguments like the ones you showed us, the scalings and self-similar solutions.
Yes, that's the point. Yeah. But I'm open to other suggestions at this point. But now for galactic sources, Nico, we can have lots of data, and individual sources may give contradictory data to this general model. But so we have to collect data from a large number of them and try to see where it fails. That's the point. And the timing property is another issue. Well, of course, following those papers, I always had the r to the -1 or close enough to r to the -1 in my head. And I realized much later that Ioannis Goddard had already derived that in his thesis, but it's unfortunate it was too late. Well, it was not too late. I mean, we're still doing this work, but go ahead, Nico. It'd be nice if somebody else comes in with some ideas and notions in that sense. And
yeah, that would be nice. I raised my hand and waited patiently, and then you made the comment about using 3 parameters for this and 3 parameters for the other and 3 parameters for the other, and we really do not learn anything. And what I like about this work and Ioannis's work is the fact that it is physics. It has physics in it, while all these phenomenological parameters teach us nothing. So, and the reason I stick with low mass X-ray binaries, with X-ray binaries and not with AGN is because we have lots of data, lots of data. And in fact, you can see a phenomenon, all these cycles that they got, the outbursts that they perform, they do it in a year or 2. So if you did not catch it this time, you'll catch it in a couple of years. And now we have several cycles for several sources. So we really have a lot of information.
Yes. Now, I'm sure that's a very interesting thing, because a few years for a galactic source, for dynamical timescale near the black hole, which is a millisecond, this is the age of the universe for an AGN. There must be physics in the outer edge of the disk. If it repeats every few years, as you said, there must be physics at the outer edge of the disk, which of course I don't know, but maybe we should consider that. I mean, we have a few of those cycles with some characteristic time scale, which seems to repeat. Then we should put some emphasis in our thinking there. And of course, the observations there won't be X-rays, right? It will be optical. What are they?
Out there, yes, optical.
Yes. So we need those too. That's the point. And we need not only the line profile above the continuum, but we need also the luminosity. I found that kind of, it has been with both me and Chris Schrader that kind of looked into this paper after paper from galactic sources. They showed some H-alpha emission, but they only show the line relative to continuum. They put a continuum at 1 and the line above that, and we cannot tell anything. Then we have to go and find what is the absolute the apparent magnitude of this source, and I haven't done that. Yes, I have to admit.
I think probably it's about time to stop.
Yes, sorry guys, it's late for you. You have to go do something, but I have dinner or something.
Dimo, thank you very much again.
Thank you. I really appreciate for your invitation, and it was nice seeing everybody.
Yeah, we do look forward to having you as a participant.
Yeah, I hope so. I hope that eventually we'll be able to travel.
Yeah. Okay.
All right, guys,
Bye,
take care.
everybody.
Thank you. Nice seeing
you very
everybody.
much.